Hello everybody, my name is Carsten, call sign Oscar Zulu 9 Alpha Alpha Radio, and I'm going to show you a couple of products I have developed primarily for monitoring power amplifiers remotely and measuring of their output power. The first one I'm going to talk about is the dual RF FET. This one is a two-channel logarithmic amplifier measuring from around minus 40 to minus 50 dBm to around 0 dBm. It will give you a voltage output that is that corresponds to the RF you apply to the ports, and it will be around 55 millivolts per dB. Output is ranging from around 4.4 volts down to around 1.6 volts, and it's inverse. So higher power means lower voltage on the output. As I said, around minus 55 millivolts per dB change. The dual RF head measures from around 10 megahertz and up to 8 gigahertz. The chip used inside is actually claiming that it will provide usable results up to 10 gigahertz, which I haven't tested. I don't have any measuring equipment for that frequency band. The dual RF head is in a small aluminum box, a milled aluminum box with SMA connectors in one end and a pluggable screw terminal in the other end with supply and the outputs. It uses 12 volts around 60 milliamps, and it has, as you can see here, it has an out A and out B, which is the voltage for the two channels, and it has an out P and out N, which is can be used for direct SWR detection. There's more of that on the web page for it. Normally you use the out A and the out B. And the next thing I'm going to talk about is my here you see the dual RF head mounted on a power amplifier. It takes its the two inputs A and B are supplied from a built-in directional coupler in the amplifier. This one is a 70 centimeter 500 watt amplifier for EME use. The next product is my remote PA monitor, or short for REPAM. It's a box that essentially is a bunch of IOs that can be controlled via Ethernet, via normal TCP/IP socket communication. So you could, if you have a remote amplifier located somewhere outside, you can, using a normal Ethernet or internet connection, you can access this box, and you can get live data from it, and you can control the outputs and so on the box. It has 6 relay outputs. You see it here to the left. They are normal closure contacts, can handle 2 amps at 50 volt DC, and they are true mechanical relays, so nothing semiconductor or anything. They're real relays. All the connectors are also pluggable on this one, so you can just remove the terminals with the cables installed. You have an Ethernet connector here. You'll see that in a moment. You have 4 digital inputs, galvanic isolated with optocouplers. You have 2 fan outputs where you can, on the label here it says 2 amp, but it's actually more like 1 or 1.5 amp per fan if they're driven at the same time. The fans can be controlled with speeds from 0 to 100%. You can do that via the Ethernet, or you can use some of the standalone built-in functions. I will cover that in a moment. Then it has a CAN bus interface. It is not supported in the software right now, but it's some of the high power power supplies we use for PAs often have a CAN bus where we can control voltage and maximum current and so on, and this is for stuff like that. It can also be for if we at some point are going to expand the number of IOs that can be controlled, those can then be controlled via the CAN bus. So this is for the future. Then there is a one-wire bus. This is for temperature sensors. The REPAM device supports currently up to eight temperature sensors. You just connect the sensors on two wires, the data wire and a ground wire, and then you just parallel connect up to eight sensors. The device will then monitor each sensor, and it can, of course, report the temperatures to a PC in the other end of the Ethernet, or it can react on the temperature in its standalone mode. For example, control the fans and so on. And then it has 6 analog inputs covering 0 to 5 volt DC, and these can be used for a lot of things. You can, of course, monitor voltage. You can set alarms. You can set triggering so that if analog input 5 exceeds a certain value, then it will shut off one of the relays, turn another relay on, make a pulse on a relay, or send an alarm over the Ethernet. There's a lot of things you can do it. You can also define alarms for the temperature sensors and so on. I'll show you that in a moment. The REPAM also uses 12 volt DC, and consumption is around 200 milliamps with all the relays connected or active and the Ethernet running. The REPAM box is also milled aluminum, conductive, anodized, and as I said, the blue connectors are all pluggable screw terminals. You have the terminals, and you have on the other side here you have the 12 volts, and you have Ethernet, normal RJ45. It supports 10/100 megabits, and there is a USB connection for diagnostic and debug purposes, which is not normally used by end users. So this is the two products I'm going to show you a live video about, REPAM and the dual RF head. The dual RF head can be configured in the software for the REPAM, so that the REPAM knows that a dual RF head is connected. And by doing so, you can define trigger points for forward, reverse power, SWR, etc. It all makes sense in a few moments, I hope. All of this is covered on my web page. Web address is moonbounce.dk, and if you go on the page, there are many different projects I have done. My antennas and so on are here described. The two products we're going to talk about today is REPAM and the dual RF head. The dual RF head, the web page is not 100% finished yet. By the way, it's an open design. The schematics are there, so you can go ahead and make your own if you want, or you can get one from me. It's up to you what you want to do. There are some measurement return laws, how it works with the REPAM and so on. But that page is not completely finished yet, but it will be soon. The other one is the REPAM, which is more complete. It's a pretty large web page because there are a lot of things to explain about it. There's also a user's manual, which is still in draft, but pretty much everything is covered in here, how it works, how you communicate with it. The interface schematics are there, relay specifications. You can communicate with it in a number of ways. using UDP or TCP/IP socket communication, which is, kind of complex and a lot of detail, but it opens up for those of you that really wants to do something with this device yourself and not use the software that comes with it. Everything is described, as I said, in here, so you can make your own applications and communicate with the REPAM box if you want, or you can use the programs that I supply. One of them, the PA monitor, which is this one here, is a free program with the source code and everything, so you can modify, change it, do whatever you want. It's written in C# in Visual Studio, and if you don't like that for whatever reason, you're welcome to do it in your own favorite language. As I said, it communicates using a TCP/IP socket and some JSON structures. So it's just knock yourself out and do some stuff with it. I supply this program for those that don't want to do their own. And I needed an application anyway for my own PA. So I'm offering it up for free. The other program is the REPAM monitor, which is basically it's just a window into the REPAM device. It will show you all the IOs. You can control the relays, the fans. You see the analog inputs. If you have a dual RF head defined in the REPAM, it will show you the power out reflected and SWR. All the settings of the REPAM is done in the REPAM monitor, and it's quite complex. There are many pages of settings you can go into. All of them are explained in the user's manual, which is available on the website. I will cover a couple of them in this video, but I won't go into very deep because there's a lot of things you can do. One of the more important thing is the trigger menus. As I said, you can define triggers for a number of the inputs, temperature, analog inputs, forward, reflected, SWR, and so on. If you have the dual RF head connected, you can define thresholds. You can define what should happen if the threshold is exceeded. You can say if the threshold should be going above or below. You can say that if you control a relay, you can let the relay go on, off, or you can pulse it for a number of milliseconds and so on. There's a lot of things you can define here. You have 12 triggers in total, and currently I only use 4 in the test setup. We'll get back to that. The fan controller. Both fan outputs can be controlled by one of 8 possible temperature sensors. I have 2 sensors installed in the system. T2 is the one that measures the LDMOS temperature. T1 measures the exhaust temperature out of the PA box. I'll show you that in a moment. You can define low temperature, low fan speed, high temperature, and high fan speed. If the temperature is below 27 degrees Celsius, the fan is off. Immediately when it hits 27%, the fan will start with 65%, up to 35 degrees, where it will be running 100%. And if it gets hotter than 35, it will of course stay on 100%. The reason why 65 is chosen is that the fans I use are not very happy at running at very low speed, so I start them up at 65. Just to make sure that they start to run, in a good way. Fan output 1 is 2 fans that cools the heatsink, and fan output 2 is a smaller fan that cools the interior of the PA housing for the low pass filter and so on. The last setting is the dual RF head. I have installed that. I tell it which of the two analog inputs are being used for forward and reflected input A and output A and output B on the dual RF head. There are some calibration boxes here, forward and reverse calibration. Basically, you apply, in my case, I apply 50 watts. I press the use button. It will then take the voltage it reads on the forward port, put it in here, and store that both. So you just click use, and then you crank up the power. In my case, 480 watts. I press use, and it saves that, and yeah, you're calibrated. You do the same with the reflected. A bit more complicated. I did it so that I turned the directional coupler, reversed it, and then I did it with the lower powers and so on. But it's the same procedure. Sorry, to the right you see the current output of the calculation, the slope of the power or the logarithmic amplifier, and you get the power shown in watt and in dBm, and you have here, that's the peak power that has been measured. You see a little bit crooked number here. That's because my directional coupler for the forward is acting a bit weird in this amplifier. There are some RF and it's very sensitive to reflected power. So this is a best compromise. It's a small directional coupler on a PCB, and it's not completely optimal. But yeah, it will show you how it works, and you get an idea of what to expect. Normally, you won't have the REPAM monitor used at all. As I said, it's only for configuring the REPAM device. Once that is done and you're happy with it, you can just forget about the REPAM monitor and focus on the PA monitor, because that is the one you will use on a daily basis. The REPAM monitor can also read and write all the settings to a REPAM device. So once you're finished with the setup, you will read the settings and save it in a file for future use if you have to change the device or something goes wrong and you need to reprogram it. That's the REPAM monitor. The PA monitor is a bit simpler. It has some settings. You can set the IP address of the REPAM device on the network. You can give it a name, and that name is what is being shown here on the screen. If you have more REPAM devices, you need to tell the PA monitor which analog inputs are used for what. The PSU input is on analog input 5. The VDD is on analog input 4. The current is on analog input 3. It will give a pulse on relay 2 and a pulse on relay 3 for on and off when you power that on and off. It has to do with the way I control my amplifier. I'm using my own overcurrent and switch protection, which is also on my website. That's a whole other idea. This is nuts. Sorry, that was a high number. The LDMOS temperature sensor is T2. External temperature sensor is T1. So that's it. The gauges, all the power out and so on. You can define the max value for max deflection, when they should turn orange as a warning, when they should turn red as an error. You do that for the power out, SWR, the IDD, which is the LDMOS current, the external temperature sensor, which is the one I said is the exhaust air from the PA enclosure, the reflected indicator, 50 watts maximum, VDD, and LDMOS temperature sensor. So this is just for defining the cosmetics of the bar graph here. We have some alarms. You can define up to 8 alarms with the text. I've only defined 4 of them, and they make sense if we go into the settings for the REPAM, because the triggers, alarm 1 will always come from trigger 1, and in that case I have selected SWR, and I want an alarm if that one exceeds 2.0 and it goes above, and then it will show alarm 1 in the PA monitor. The same for trigger 2, alarm 2 is high temperature if LDMOS exceeds 60 degrees, and analog input 3, if that one exceeds 20,000, it will give an alarm and say high current. We'll get back to that. And input 4, the forward power, if that one exceeds 550 watts, we will get the alarm high power. Now the analog input 3, I set that to 20,000, and it's in millivolts. That's 20 volts, but I just told you that the input goes from 0 to 5 volts. So how's that gonna happen? All the analog inputs can be scaled, so that in my case I measure the IDD for the LDMOS across a shunt resistor, and the shunt resistor is a 1 milliohm, and the circuit around it, the amplifier that sits on that one, will give me approximately 50 millivolts per amp. So by multiplying the AI3 input, where the LDMOS current is measured, by 21.11, that's of course calibrated, but ideally it should be 20. But by multiplying that with that number, I actually get this one. Now it makes sense, because you see the AI3 will be multiplied so that I know that each millivolt measured on the AI3 when scaled correctly with the AI scaling, that will correspond to 1 milliamp. So by entering 20,000 here, I'm effectively setting a threshold of 20 amps. And alarm 3 will sound when I get above 20 amp for the amp. So that's how it works. So the scaling is important, and as you saw here in the PA monitor, the PSU input and the VDD inputs are both on AI4 and 5. And if you look here, AI4 and 5, they're actually multiplied by 16. That's because the PSU is delivering 52 volts DC, and you can't put that into the analog inputs on the REPAM. So there's a resistive divider that converts the 52 volts down to 3 point something volts. And by multiplying with 16, I again, let me show you, if we go out here, again you can see down here AI5, it shows now 52,000 millivolts. So that's the 52 volts from the power supply, because it was multiplied by the AI scaling. So this is a way of making the numbers on the analog inputs understandable, and so that they make sense when you define the triggers. 20,000 milliamps and so on. You could also make one for the voltage. If that one exceeds 55 volts or 55,000 millivolts, then it would shut off by pulsing on an output or whatever you want. So that you can define the triggers in many different ways, and you can accomplish many different things using the triggers. So back to the PA monitor. This was how this was defined, and how you select which input is used for what gauges and alarm texts. So that's it. I'll show you a little bit about how the setup is running. I have a camera sitting here that shows you right now the bird watt meter. I will try and see if I can show you just an overview of the PA. You see the REPAM device sitting here. This is the whole PA construction. See if I can move this camera around. Everything is inside the box, sitting on a very large heatsink. the PA will be mounted at the tower. That's why it looks like some industrial industrial setup. There is a power supply sitting there at the end for the 52 volts, and you can see the the dual RF head is sitting there and measuring forward and reflected power from the PA. The cables and so on will of course be beautified when mounted in the box, but for now it's just it's primarily for testing the stuff. So let me start by powering up the amplifier. Right now the power supply is on. You can see around 52 volts, and if I press this one, you can see the VDD jumped up to 52 volts. So now the PA is actually powered on. Yeah, you see the current is basically it's zero. It's not drawing any power. There's no bias. The temperature on the LDMOS 25.7 and the external 25.3. And then let me try and give it some drive. This is from my IC 9700. You can see that the power goes up, and you see the power, and you can maybe hear that the fans are starting to spin up. You see the power going up and down. You can see also the efficiency. And you see the IDD, the current for the LDMOS. You see the LDMOS temperature is rising now, which is natural. Yeah, let me switch it off again. So you saw the power go up and down. Everything looked perfectly fine. Let's try and do a small thing with the triggers. Let's define trigger 5. Let's say that if the forward power exceeds 300 watts, we want just an alarm if we go above that. Okay, so trigger 5, forward power from the dual RF head, 300 watts, we want an alarm when it gets over. Okay, so we send that out to the REPAM. It just warns me that you are about to send all the settings out. Yeah, do that. So we have now defined the 300 watt alarm marker, and I will go and transmit again. Slowly turn up the power, and once I cross 300 watts P out, you will see the alarm go off. And you can see when I cross, it will go from yellow to red. Yellow indicating that there has been an alarm, and red that there is an alarm currently. Okay, so and again you can acknowledge the alarm by just clicking on it. This is just to show you very briefly how the triggers work. As I said, you can use the triggers for activating the relay outputs. And one thing to bear in mind is that all this trigger and fan controllers, that is handled autonomous in the REPAM device. So the PC programs does not play any part of it. So even if you had an Ethernet connection that broke down, or you lost your internet to your remote site where your amplifier was located, the REPAM will still control the fans. It will still, for example, activate an output if the SWR got too high suddenly, etc. So you don't need a PC connection as such. The REPAM can do a lot of things by itself without the PC connection. Especially handling fan controllers and shutting down with high SWR is super important. And the triggering on the SWR and the analog inputs and so on are very, very quick. I mean, we're talking about 1 or 2 milliseconds of reaction time. So they are done with high priority inside the REPAM because they know they need to react very quickly on certain things. Yeah, that's the triggers, the fan controller, and the dual RF head in the REPAM monitor. As I said, REPAM monitor is not used for every day. It's only for configuring and doing stuff when you set up the system. The PA monitor has another feature which I quite like. It's possible to store the data, log the data, the live data every second to a comma-separated file, a CSW file. Now I have started the logging, and I will go and do another transmission. Just play a bit around with the power. Go up, yada yada. You see the temperature rises. The fans are now starting to run, and we will stop transmission, and we will stop the log data. So if I now take a short moment, I will just find, you see I brought in here Microsoft Excel, and I will find the data I just saved. Let's see, we go to, sorry, it's in Danish, but yeah. Where is it? Where is it? Where is it? From CSW. You see, so I selected the CSW, the text file we just got, and Excel will it knows the format, so it just read in the data. And here you have the log of the data. For every second, it makes a log: forward reflected SWR, IDD, VDD, PSU, efficiency, LDMOS degree, and external degree. So now things are getting interesting, because if I select, let's say, the power out and the IDD, and I make a graph here. Now we suddenly have a graph of the power and the current. So let's say that the current, we put it on the secondary axis. So we have the current, hold on, make it a bit wider. The blue line is the power out. You have it over here, and the orange one is the IDD. And let's make another one. We can take the forward power and we can take the efficiency. And we go down here, and we want to have another chart. Get it here. This is then the efficiency versus the output power. Again, we will put it on the secondary y-axis. So now the orange line is the efficiency in percentage, and you see the efficiency above 300 watt output, the efficiency goes up. And if you are, let's say you're at 130 watts, your efficiency will only be around 35%, whereas at full power it will rise to almost 60%. So this is This is a simple tool that will allow you to assess if your amplifier is working as it should. If the temperature is stable, we can see here in this short test that the temperature naturally will rise. But what happens if you, for example, have if you have a PA? Let me show you that from the user's guide for the REPAM. This is actually interesting. This is the orange one is the LDMOS temperature, and the blue one is the power output. You see the power output goes up to around 475 watts. This is simulating Q65 EME on 70 centimeter with the PA you just saw. It transmits for 1 minute and it receives for 1 minute. And by looking at the temperature, you can see that it rises. The orange one rises to begin with, and then the increase in temperature for each transmission period goes a bit down. It doesn't rise as fast. And by letting this run for like 30 minutes or so, you can see where the temperature will stabilize. So you have an idea if you have enough cooling and so on. So the tool, the logging of data can be used for many things. This is just some of them. You can also you can look at, of course, the forward power and the IDD. You can also see the power supply. Is the voltage stable enough? You can see here it only drops about 0.2 volts, which is okay. You see both the LDMOS and you see the output power from the voltage from the PSU. So this gives you a nice view of some of the parameters for a power amplifier you have. And this is just another usage of the data. So that concludes my presentation. Again, go to my webpage www.moonbounce.dk, and where you will find these two products and some other things that I have done. I said that the overcurrent and switching on off of the PA is also something I did. That's also explained in here with schematics and BOM files and Gerbers, so you can actually make your own PCBs, which quite a few have done so far. Go in and have a check, look what's going on, and let me know. As I said, I will have a limited number of dual RFED and REPAM devices available for sale, but you can find more information of that on the web page. Thanks for sticking with me this long, and enjoy your day. Bye-bye.